Let's welcome Doug to stage.
All right, it's great to be back at SPIE XR. I've been making this trip for the last 3 years, and it's starting to feel like home. I really mean it. I've spent most of my career between fields without one conference to actually call home. Something like the varifocal displays you'll be hearing about don't exactly fit in one event. They span optics, computer graphics, vision science, and the same goes for computational displays, which I'm most known for. So I want to thank Bernard for growing this event and building a home for all of us working on near-eye displays. Now, the best way to thank Bernard is to show up and actually tell you something new and share it with the community, so I will. I've been at Facebook Reality Labs for about 5.5 years, building what's called the Display Systems Research Team. I'm very proud that FRL allows us to speak widely and freely about our work in the hope of driving this industry forward. Over the last 3 years of this event, you've heard a lot about the half-dome prototypes shown here, and you'll learn more today, but to follow through on my promise to Bernard, you'll also hear about brand new work in high dynamic range displays, as well as retinal projection. DSR is full of researchers that are driven to prototype emerging display technologies and to share those prototypes through publications. Here's a selection of some of our work. You can see we're deeply committed to achieving eyeglasses form factors using whatever means necessary. A lot of our work involves computational displays, but sometimes it involves just really great engineering. But we have been looking for a receptive community. To date, that's always been SIGGRAPH. People often ask me, why do you publish display work at SIGGRAPH? Isn't that a computer graphics conference? Well, in this talk, I'll try to convince you that displays are the hardest problem in computer graphics, and that we've been on this road for a long time, and that's why the work from my team isn't just rendering, but it's largely trying to solve the remaining challenge in graphics. And so, any good team needs a mission statement. And I and Gordon Wetstein, you heard earlier today, share a mission statement. It's very simple. It's shorter than an elevator ride, so it's not even an elevator pitch. We want to pass the visual Turing test. We want to build cameras, rendering algorithms, transmission, compression, storage, and reconstruction and display algorithms end-to-end that make reality recreated flawlessly. Now, it's not just because we want some great telepresence system. If we can deliver to the human visual system everything it needs, then we can do the more interesting thing of going on an adventure to any reality. And that's what Ivan Sutherland spoke about when he kicked off this entire field. So let me convince you that displays is the heart of computer graphics today, because let me show you what modern computer graphics is. It's unimpressive because you've all seen it for so long. If you have enough compute, enough power, and enough patience to wait for the frame to be rendered, you can have photorealism. And you could have it years ago. You may not notice if I didn't point it out, but of course, that car there is synthetically rendered. And increasingly, real-time computer graphics, even mobile graphics, will catch up to the state of the art. So those of us here at conferences, we're about the bleeding edge. Where's the low-hanging fruit rather than the tail end of research? I think it's here, because every time I walk into an electronics store, I see what I saw in my childhood. Sure, CRTs became LCDs, but they've always been flat, glowing rectangles on a wall. They're now retinal resolution. We're pushing 1,000 nits. Color gamut's getting a little better every year. Frankly, this is getting boring because we're not pushing forward the frontiers of display technology. And so 5.5 years ago, I decided maybe we've had enough with rectangles on a wall. Let's see what we can do with a real display technology that allows you to experience everything the human visual system is capable of sensing. And so I think this is why I and many of my team have committed to virtual and augmented reality. It's not because it's a toy or interesting. It's because it's the only display technology we can imagine that can deliver the full human experience. And what is the killer app? That's always the question, even today in the hallway. What is the killer app of VR and AR? I don't think that question is actually that hard to answer. Because if you think about VR, it's 3D. 3D interaction, 3D audio, and of course, 3D display. And so in the Display Systems Research team, we try to start with the basics. So ask a vision scientist, what is it we need to do to completely stimulate depth perception in a human? And they will point you to this paper. Vishton and Cutting, in 1996, did a large study of the field, and they looked at all the cues that could stimulate depth perception. You've probably seen this. Textbooks usually have what's on the left, a list of depth cues. Aerial perspective, binocular disparity. You've heard all of these. If you read the Cutting and Vishton paper, what's so fascinating is they ask a simple question: why so many? Because if you think about the other human senses, perception of sound, touch, taste, they don't use nearly as many multisensory cues to try to synthesize the signal. So why is it? Well, Cutting and Vishton argue it's because depth perception lives across 3 different spaces. What TVs have been doing for so long is what they call the vista space. Walk outside, go on a beautiful walk to Telegraph Hill, you'll see the vista space. You'll see the skyline and the rolling clouds. The thing is, we've been solving the display problem for the vista space for decades. Occlusion, relative size, aerial perspective, and so on. We can depict those perfectly on modern televisions, and we could years ago. So again, I don't think it's so hard to answer what the killer app for VR is. It's to live in the space humans do, and that's called the personal and action space. So what is the action space? Well, it's the distance I can throw this remote and hit you with some accuracy. That's the action space. The personal space is, of course, where I can reach and interact. This is why VR and AR is so interesting, because televisions cannot do this. But with VR, it's trivial. Getting binocular disparity, motion parallax right, yeah, we do that. That's table stakes. So looking at this table, talking with your friendly vision scientists, you realize there's one thing missing. And it only matters in VR and AR, and that's convergence and accommodation. Many times in an event like this, there'll be questions of, why work on accommodation? It's so subtle. Vishton and Cutting agree with you. It's the least important depth cue, but for a scientist like myself, it's the one you have to deliver to even know if it matters. So we set a goal many years ago now to build the world's first complete display system that depicted accurate convergence and accommodation cues. And it really could only be done at a place like Display Systems Research, where we had the engineers to make that control system work. And so you'll hear more about this today, but I just wanted to give you a framing. And then what I've learned is it takes an army to do something like this. And so you need inspiration, right? I began life, my professional life, as an academic working in graduate school. I didn't have the ability to marshal a team against this. I needed some path to follow. And there's only a few inspirations to take, so if you're going to take one, take it from the space agency. So how did NASA put a buggy on the moon? Well, they sort of rushed the job, and by the late 1960s, they said, we really need a more formal process. It was sort of a chaos getting that moon buggy there. What are we going to do? The program managers in the audience are smiling because I'm about to justify your existence. You climb a ladder. And I know sometimes you don't want to put yourself in a box as a researcher. You're like, I could do it. I could ship a product. NASA would disagree with you. Everyone in this room lives at different rungs of the ladder. If you're an academic, you generally work on levels 2 through 4. If you're a real deal scientist, you're at level 1. The startups out here that we're hearing so much from, they believe that they need to bring this into the world. They work at level 6, 7. And then those of us in the big companies, we're like fully bought in. We go to China, we go around the world, and we work at level 7 and 8, 9, and we ship this thing to everyone in the world. But I mentioned I and my team, we're your classic level 2 through 4 people. So when I was at the MIT Media Lab, together with Gordon, we loved working at this level, right? We had a hammer, compressive displays. And we said, wouldn't it be great if we built the best glasses-free 3D TV ever made? So that's level 3. And then wouldn't it be great if people cared? But of course, you do this. In your career, you start in graduate school, and you do level 2, 3, and 4 over and over and over. And at some point, you walk into an electronics store, and you see level 9. And you start to wonder, am I just going to do this cycle of level 2 through 4 forever? How do I actually change the world rather than just have good ideas? Well, at MIT, we had one solution. It's the best solution if you're an academic. You hope someone else does that hard work. You write a paper and do a Google search. I checked. 100% of the papers I wrote when I was at the Media Lab and afterwards, the conclusion ends with the exact same statement every single time. We hope to inspire others. We hope to inspire others because we're having way too much fun working at levels 2, 3, and 4 to commit our lives in a startup, to commit our lives in a major company, to spending a decade bringing this clever idea of a compressive display into an electronics store. So I've reached, in a sense, my mid-career point. I'm very blessed to have a large, excited team at Facebook Reality Labs. And so this is corny, but I realized we have to work with a higher dynamic range. And so what's really unique about this display systems research team is we're not quite a startup, we're not quite a major company, and we're not quite academics. We really play from the absolute fundamental vision science through very polished prototypes, more polished than you'd see from most startups, to try to do one thing, which is change what's in that electronics store, but we're allowed to talk about it. We are a bizarre bunch. It doesn't exist much in this world, and so I'm so grateful to get to talk about the work we do. So let's dive in. You're at a technical conference. That was just a presentation for the program managers in the room. I do love you. Thank you for being here. Now, I'm going to speak to the scientists. You're like, I get it. Give me your level 2 stuff. Well, I'm going to give you something better than that. Let's give you the latest update on varifocal displays. So we spent, at this point, more than 4 years making the thing on the left. I would argue, because I'm so proud of it, it's the world's best varifocal display. 140-degree field of view, integrated eye tracking, absolutely silent varifocal. It's a cool thing. Very cool. But of course, we showed it to the world a while ago knowing there's always something better, right? If you're a magician, you always got to have your next trick. And so we were very proud a few months ago to show Half Dome 3, because it's not a product. It's level 6. It's something that is not quite a publication. It's beyond that. And this thing is more like level 5. It's almost ready for prime time. So let me tell you about it. Half Dome 3 is an ultra-compact VR headset built using folded optics and no moving parts electronic varifocal. So again, I really love being transparent. This is the thing. Feel free to copy it. These are the motors and the mechanism by which we did Half Dome 1. On the left is Half Dome 3, where we said, look, we now know, we have our demo. If we were a startup, everyone now believes varifocal is worthwhile who's tried Half Dome 1. Let's get rid of the motors entirely. And fortunately, we have wonderful postdocs, interns, and liquid crystal scientists who are constantly having lunch together. And over the last 2 years, an idea that started with an internship, with scientists planting seeds years before that internship, turned into this. I think a very pragmatic way of solving focus in VR. It's a stack of liquid crystal elements, pancheratinum Berry phase lenses, intermixed with switchable half-wave plates. Things you could expect from the display industry that with extremely great care by the optical scientist and others sitting over here, put into a really wonderful module. And so let me take you through it. First, you have two-plane. Two-plane is sort of the state-of-the-art in the industry. So let's see how we do two-plane. By changing the voltage on the switchable half-wave plate, you can focus near. You can switch to focusing far. This is showing a see-through scene, but of course we designed this for VR. So you got a pair of digital bifocals. That's cool, but we started life building continuous varifocal systems because we want to pass the visual Turing test, not that this is the minimum viable product test. So we needed a way to create smooth varifocal, and this gives it to you. By stacking 6 elements, you grow as the power of 2. You get 64 focal states. This is a real video, obviously a good video. We were careful in how we assembled the components. And if that's not enough layers, add one more switchable half-wave, one more PVP, and you'd be at 128 states, 256. At some point, the human visual system, according to Marty Banks and others, just could not resolve the difference. So that's what an electronic varifocal system could look like when you start from first principles and you ask, what could I do with VR, where the light source is polarized, the illumination's polychromatic, the resolution is not retinal resolution right now. You end up with something like this, tailor-made for VR. And you show it to people. And here's what it looks like. This is shot through a real prototype with all the challenges that real prototypes have. And like every other startup here, you see nothing, because that's our goal. You don't notice flickering, changes in brightness, changes in color. And of course, that took an army of researchers to make that happen at the level 5 capability. OK, so that's great. Being in a startup with no risk is an exciting thing. I recommend it for all of you at some point. That was our startup. Now, we're scientists. The reason we wrote those papers is we like to play at the beginning of the phase, to have wacky ideas and see them through. So I want to share some new wacky ideas with you that display systems research believes is part of this mission of passing the visual Turing test. First is something near and dear to me. I've told you several times in this talk that I walk into electronics stores and I'm disappointed because I keep seeing the same televisions over and over. I will tell you, The time I walked in and first saw a high dynamic range TV, I perked up. I said, good, 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 this is something. It felt like the moment I first saw an HD TV. It felt like something new under the sun. To date, no one has tried HDR in VR. There's a good reason. It's hard to do. We don't even know if it matters. I love working on problems that we don't know if it matters. Do we know if accommodation matters? We'll find out. Do we know if HDR matters? Well, I certainly know it makes a great experience, but someone has to build it. And that's the type of work DSR loves doing, or at least I love doing. The thing we want, of course, is brighter brights. I really do want to go to a beach in VR and be blinded by the sun. But of course, I want to see blacks blacker than they are. Now, to sell this to someone, you got to tell them it's not just about not wearing sunglasses in VR. So take a luminance meter, walk into a normal office environment, and you'll find out that VR does not create the range of luminances needed. Just looking at the back of a monitor is more than 2.5 times brighter than the brightest VR headsets. So we're living at about 100 nits right now in VR. The best consumer TVs are around 2,000 nits. Obviously, they're hooked to a wall socket. They're way thicker than you could probably do in the backlight of a VR headset. And of course, to get true reality, we're looking at 1 billion nits. Right? And in AR, we worry about, can we take 1 billion nits and maybe get one out? So it's a very different problem in VR that we want to preserve the 1 billion nits. Again, this is early stage work to drive this field forward. Here's what Yang Zhao and interns and others came up with in our team. They said, look, from first principles, we know a few things need to change in HDR VR. First of all, we should be careful with our light. Start with a light source, LED, whatever it is, collimate it, pass it through an engineered diffuser. This gives you what's known as a directional backlight. Because VR is unique, unlike those TVs on a wall, they only have to work for me and only for one eye at a time, which means every single photon can be aimed at the eye box. That's going to help with brightness. And then you can take the old trick of dual modulation to get contrast. But here's why you haven't seen a VR headset yet. You need an eyepiece. And if you use a Fresnel lens or some other optic, you will usually lose all the contrast you created through this dual modulation scheme. So we built a time machine. That's how a lot of our work begins. It's level 1 because no academic committee would accept it. It's too basic. But we need to see if we believe HDR is worth doing. So here's what we built. A DMD projector combined with an LCD you'd see in a VR headset. This is a Seatson high dynamic range display. But then we combined it with a high contrast eyepiece. Not a Fresnel lens. It's too big, it's too bulky to be in a headset. But it preserves the brightness and contrast at the 6,000 nit level. Stare down the barrel of this thing, and you'll see an extremely good HDR TV, because this is not head-mounted, it's not tracked. It just shows us that the components are possible, that the eyepiece can preserve the contrast of the display if you're willing to have an enormous, bulky eyepiece. So you got to ask, have we built a headset you can wear? Almost. We are here to share our work. And so what Yang Zhao and his intern have published is this. The first step towards creating the world's first HDR headset, and it's a folded optic. By starting with a Seatson-style projector, you can couple into a light guide. Be careful in that design, and you can fold everything. This you could get on your head. So again, we are researchers. We will do the startup thing. We'll wow you with varifocal devices. But what really gets us excited is this stuff, the very beginning of even knowing if it's worth working on. All right, I want to tell you about one more project. You can read about this one in the paper. Many of you may be skeptical about VR. And so you're here because it's an AR conference. Well, I'll tell you, my team is split. Some, like me, believe VR is the greatest storytelling. It's the ultimate end of such a long chain of history of trying to capture and recreate reality. It is SIGGRAPH. But AR is interesting in its own right. And so for those publications you saw earlier, about half of them from my team, both before and after they joined FRL, are focused on the goal of making AR glasses. And glasses, wide field of view, big eye box, beautiful system. And many of these approaches we're taking are not waveguide displays in this work, but of course the alternative, which is retinal projection. Andrew Mamone on our team pioneered recently the idea of using a holographic near-eye projector off-axis with a holographic lens, like doubled down on holography, to show you can create very wide field of view AR glasses. Many of you should be familiar with this work, and if you aren't, a quick Google search will solve that. You'll love it. It's an amazing piece of work. The only problem is étendu. Of course, in that work, he achieves a very wide field of view, but you got to look hard in the paper for the eye box, because the eye box really isn't there. So that's the problem with retinal projection right now, is if you turn the knobs, you can have a big field of view but no eye box, which means the second you put this thing on, the image disappears. Or you be more practical, you turn the knobs so that the excitement is lower, you get a not exciting field of view and a sort of okay eye box. This is one reason we're not seeing a lot of free space retinal projection on the other side of this wall. Most people are working in different design spaces because they haven't quite cracked this étendu nut. And we're looking at ideas, very early stage, again, to inspire this entire crowd, not just to drive our company forward, but to encourage people, maybe there's something in this direction. It's why Andrew published this in the first place, was to try to encourage maybe some work on free space would be interesting. So here's a solution. Of course, we can go back to the wide field of view design, let the eye move, and you know the solution. You've all heard it at this point. It's varifocal in a different way. If we have an eye tracker and an adaptive optic, we can steer that exit pupil. It's like the foveation concepts you heard. Again, it's like the varifocal systems. It's this control loop being solved by adaptive optics and eye tracking working together. Pupil steering, if it worked, potentially could solve the problem of retinal projection. I'm sure many of you are working on it. You may not be so free to speak about what you're working on. I hope you solve it, because this could actually be a wonderful way to solve AR. Many of you who are working on it are probably working on it the same way we did. Levels 2, 3, and 4. You got an idea. How about we put a laser array on the temple of the glasses? How about we use a really exotic HOE? This is what I love talking about at lunch. You will find 50 ideas in 1 hour. If you ask someone in an interview, you'll get fewer ideas but better ones because they're trying to get a job. And if you ask a full-time researcher, you'll get even fewer ideas but perhaps one that works. This is not a bad way to try to solve research questions. But again, I think inside of industry, I have an opportunity to work at a more fundamental level. So on our team, we actually started at level 1. We hired a postdoc, Kavitha Ratnam, and we asked her not to try to think about how you would steer, but what the requirements for that steering would be. So starting from first principles, Kavitha, working with Robert Conrad from Stanford, started with the eye models you all know and love, and asked a simple question. Do we need to steer? Yes. Do we need to steer just in 2 dimensions? Do we need to steer as the eye moves in 3 dimensions? For instance, as your eye rotates in the eye box, the eye relief will change. Do we even need to steer by changing the roll, tilt, and yaw of the projector, or at least 2 degrees that are non-redundant? To our knowledge, no one's looked at this simple question. Everyone's jumping to levels 2, 3, and 4, so I think you got to start with the basics. What is the size of your exit pupil? What is the size of your entrance pupil? And what degree of steering do you need? Because if it's 5D, this is going to get real hard real fast, and maybe everyone working on other architectures is right. So I encourage you to look at Kavitha and Robert's work. They've built an end-to-end Zmax model where you can study vignetting, MTF, and simulate the requirements. So when you saccade, is it OK to lose half the image or not? These are simple questions you can ask. Read about it in the paper. And on time, right to be kicked off the stage, the summary slide. So that's my update on display systems research at FRL. After 5.5 years, we're having a lot of fun working across a broader scope of research than many of us have in the past. Starting at level 1, we're trying to push fundamental vision science to drive requirements for our systems. We still have plenty of not quite ready for prime time ideas at levels 2 through 4, and occasionally we dive into startup mode. We do things at level 5 and beyond, like Half Dome. We're so happy to get to pull back the curtain here at SPI EXR. And of course, we hope to inspire others.